How's it going? I think I'm the significantly post-lunch infotainment. So I will not have anything which is explicitly GNU Radio, but lots of things that I hope tie into GNU Radio in the not-so-distant future. More specifically, I'm really sort of saying you're in the right place because this the sensibility of software-defined RF systems is clearly the future for lots of reasons. All right, so yeah, you saw I do a bunch of stuff. We'll talk about this as we go along. All right, so if we think about the future of needs, you know, I have this sort of thing where this cartoon of a smart sort of city with integrated sensing and communications. Not long ago, this was all sort of just academics talking about doing stuff, and now there's a fair amount of interest, which you can see going into 6 and future G, about how do I use RF energy in more intelligent ways. I'll come back to this as we go along. So what else do we want? So we want more functionalities, of course. We want everything to be more flexible, more useful. We, of course, want lower cost, size, weight, and power. I was amusingly at a meeting now 2 weeks ago where someone's solution for a radio system was going to cost 100 kilowatt, or sorry, a kilowatt. And I was like, you can't do that. That's burn your hand off. Anyway, so next generation of wireless systems, for reasons we don't understand, we're going to hook up everything to the internet, including toasters, which that's a real thing, by the way. That's not like a cartoon toaster. There is an internet toaster. Clearly, we're going to integrate in our base station systems or cellular systems into satellites as well. You can just see that. You can already see people starting to move in that direction. Autonomous vehicles. There's lots of P&T issues, communications, reliability issues associated with that. Once again, people are spending a lot of time thinking about those sorts of topics. Augmented reality is a really interesting problem because it's a mix of local processing, local P&T, and then stuff that's far away. And so I need to worry about communications, I need to worry about how this stuff working. And the loads are all going to be dynamic, and the applications are all going to be dynamic. The notion of a single function system will not survive very long. One of the things we do in my lab is we generally call it cardiac radar. So we do use small scale radars to estimate things. We can actually, the blue line you see there is an individual heartbeat measured remotely using a radar. So we measure the R-to-R intervals. We actually now have papers where we have measured the sound in the chest remotely using a radar. Anyway, you can imagine using the RF front end for a cellular system. Now it's multifunction. Your phone could also be measuring your health remotely and in ways that a wearable system like what's on here just can't do. And then, of course, we sort of enjoy cats for some reason, and so you know at some point we're going to have some augmented reality cat simulation system, which is going to lay over the course of your real life. You can imagine cats all over the place here. It's just going to happen. It's not my fault. All right, so thinking about what the future holds, right? So we're going to have multifunction systems. I'll talk about that a bit more. We're going to have integration of cellular systems from the kind of traditional cellular systems and satellite systems. It's going to be always best connected, right? You're going to be moving through these systems, and you won't even know what's going on. Once again, from your perspective, this is a highly dynamic, flexible RF system that you have to have. How do you actually do all these sorts of things, processing the RF signals, constantly changing, right? Right now, the modem processor in my phone, while incredible and a work of art, can do one thing, right? It literally switches to a different processor if I switch standards. Forget about trying to switch really fundamental things that I'm trying to do. Distributed coherent base stations, these sorts of things are coming. I'll talk about that a little bit more. And then, of course, we're back to the internet toaster for some reason. So when I talk about the idea of spectral convergence, once again, this is where GNU radio capabilities come into play. I want to do multi-function systems. I want to be able to enable functionalities that I didn't even realize were available before. So once I start mixing sensing, positioning, navigation, and timing, and communications in a flexible RF use environment, right? I open up applications that people didn't even realize were things that were possible before, right? So my phone is now a radar. I'm actually can potentially sense the attention of people that are watching me by watching the fluctuations in their heart rate, right? I can maybe have a sensing of augmented reality, identify the people that are falling asleep. I know who you are. Out in the audience, right? While it's augmented, because I'm doing the sensing of the RF energy all at the same time. It's overlaid in what I'm doing. Very precise positioning, navigation, and timing, which would be required for doing interesting augmented reality, right? I'm going to try to do all these things. To do this, though, and do this intelligently, I've got to do this very flexibly. And, of course, so it doesn't have a kilowatt sitting on my forehead. It has to be incredibly efficient, right? So we need to sort of solve all these sorts of things. And when I have multiple RF functions happening simultaneously, I want to improve the overall system of systems performance, not have these being competing systems that degrade each other's performance, right? So this is an active area of research right now. There's certainly examples where we've made lots of progress. We can do simultaneous communications in radar. We can use communication signals to do radar. Things that historically would have been considered interference that causes the entire system, both systems to fall apart, we easily disentangle now. So multi-functions in the same spectrum we can do. All right. So I sort of already talked about the idea of having simultaneous, using my RF system, my millimeter wave front end for gesture control or being able to use it as a radar. There are lots of automotive applications. I'll talk about one in a second. And then there are lots of military applications as well. All right. And these ideas are all enabled by recent technical advances. Some on the RF front end side, which I will talk less about because I'm more on the algorithms and computational side. But that all the RF front end work is incredibly important. But I think you're probably more on my side as well, trying to figure out how to implement algorithms on computational systems. All right, so just once again to sort of motivate this idea of I would like to have a simultaneous system or a system that does multiple functions simultaneously. So some of you may know that there is a standard for how cars talk to each other. It of course, is an entirely separate system than the system that cars have, which are pointed at each other, which are radars. If you think about it for just an instant, you're like, why do I have a full system intended to point at the car in front of me, but when I want to talk to the car in front of me, I'm going to build an entirely independent system to talk to the car in front of me? It makes no sense at all. But our radar system is not built so it can talk to the car in front of me because it's too dumb, right? So it's a clear opportunity. The RF energy is there. We can do all sorts of things there. So imagine a scenario where we have multiple vehicles. We have some legacy vehicles that are not connected to the network. We have vehicles which can talk to each other. In this particular case, I have a legacy vehicle that's going to run a red light or whatever it is. And the car behind it, which is tracking it with a radar, goes, I see that car is going to run the red light. I can simultaneously use the same radar energy / comms energy and talk to the other car, which is now here vehicle 2. And while I'm talking to it, using the same energy that I'm using the radar in front of me, I can also do relative P&T. I can get insanely precise positioning of that vehicle because it's working with me. So it turns out if you do timing strange techniques, two vehicles are talking to each other, you can get timing. There was a discussion of actually doing distributed coherence. It's the same sort of technology as that. We can do that over RF. At the same time, that vehicle number 2 can then talk to vehicle number 3 and say, there's a car running the red light, you can't see it. It's hidden by the building, but it's coming, and I want you to be careful. All right, so in order to do this, you have to make some trades, all right? This is just a notional theoretical result, but I can do everybody's favorite radar waveform here, which is chirps. So I can do various pulse chirps. I can actually do the communications we're using pulse position modulation. I can do the relative P&T between the vehicles using same sort of techniques. In this case, I assume that it's not particularly intelligent system, and I'm separating some of the users by having different spectrum. And then what I can do is I can do an overall system optimization where I get really good relative positioning, really good data rate, and really good ranging from the radar information as well, right? And it turns out that I can work out the theoretical performance bounds, and I have this manifold of theoretical performance bounds, which are pretty much pretty close to being achievable, where I can move along there depending on what my system needs at that moment, right? And so in general, this is one of the things we think about, which is I have multiple functions. I'm going to figure out what the manifold is and what that manifold is of joint operation of all these functions, and then my system can move along there, and my RF system has to change its functionality and its processing dynamically to deal with this. So once again, software-defined RF systems are the only way to do this. All right. So we're working through this. This is a real thing that we're thinking about. And once again, I already said it. This is why you're in the right place, which is thinking about software-defined RF systems is the right answer for like the future of how we're going to use the RF. We already talked about the range of broader use. So one of the concerns here that immediately comes up is everything I'm talking about is relatively expensive computationally, and it needs to be flexible. So you know, if you think about sort of types of solutions for processing, currently we're sort of in trouble for lots of systems. Like, so when your phone is downloading the 4 simultaneous cat videos using 5G, you feel it get a little bit warm. The modem processor is actually burning about a watt. So it turns out the answer, the limit you can actually have is about a watt. So if you use a general processor, this is a disaster, right? You can't put it in a little package. So that sort of processing doesn't work. And you can actually think about, well, what about FPGAs, the next step up? Certainly an improvement for a certain class of things, but still FPGAs are very power hungry, and don't make me make fun of GPUs. So, you know, great for what they do, but once again, still a wrong answer. That's not what we want. We would like to be able to get something close to that modem processor, which we all grown accustomed to, but it's single function. It can only do one thing. You change it a tiny bit, you have to go buy a new phone. All right, so that's what we're thinking about. So if you take a look at the computational performance in terms of power, so I would like to do something interesting. Interesting things are half a teraop per second, right? Really interesting things might be several teraops per second. Right? So you know, serious problems. You're trying to do that with a general processor, right? It's hundreds of watts. Your phone, once again, the modem processor in your phone gets to do it for less than a watt. And because it's single function, it's designed to do one single thing, that does it very efficiently. And what you see on the plot in the upper right is sort of a surrogate for time, which is actually node or feature size on the IC. We are now heading towards 3 nanometers. Most of our work, by the way, is at 12 nanometers. And you can see that the full custom ASIC is more than 2 orders of magnitude more efficient than the general processor. And basically everything else still doesn't work so well. So we have had a DARPA program for quite some time where we've been working on doing a processor, working on developing a processor to try to address these problems. And in general, you can't. I mean, general processors are rather power hungry because they're general processors. They got to solve all problems. And so there's this trade. So the trick is to recognize that there are a domain of operations. And if I focus on a particular domain of operations, in fact, there are a small number of computations which are the expensive ones. And there's lots of busy work, right? So that's the idea here, which is if I take a look at a multi-antenna receiver system, it turns out expensive things are matrix multiplies, QR, back substitution, the forward error correction, and filtering, and these sorts of things. And then there are a gazillion other operations which in fact are really boring and don't actually take a lot of effort. So the answer is clear. Make the hard stuff efficient and don't worry too much about the rest, right? Don't sweat the small stuff. Okay, so that drove us to, there we go. That drove us to designing a SoC with an architecture, which is a coarse scale heterogeneous processor. It has a number of ARM processors for the boring stuff. We have full custom, but flexible FET accelerator, FIR filter accelerator, and we have something which we call the DAP, which I didn't really explain, but it's a systolic array processor, which is very good for doing linear algebra sorts of things. That goes back to our matrix multiply, our QR back substitution. It basically was within a factor of a couple of full custom, even though it's actually completely reconfigurable. I can reconfigure that, not like an FPGA where it might take many seconds to reconfigure. I can reconfigure the DAP in the order of a few hundred nanoseconds, and it's also much more efficient than an FPGA. It's because it's a little more limited in what it can do, but it's the stuff I care about. And then we have some flexible FEC accelerators as well. So a range of FPGAs, polar codes, anything where you have this sort of message passing decoding. We're very efficient. We tend to be on an order of a factor of 3 from full custom implementations, but those full custom implementations do a single code type with very little flexibility, and we're pretty close to it. So, great. Why doesn't everybody do this? Well, one, it's kind of weird to ask so many different things of RF historically. It was hard enough to get anything to work. Goodness knows, trying to get something which does everything was just too much to ask. But now we're starting to ask that question. That's one reason. The second reason is that a few people have built coarse grained heterogeneous processors, not as good as the one we built, or we're working on right now. We have a tape out in 6 weeks. But the problem is that the programming, the threading of the data through the chip is so complicated that literally there'd be a person on the planet who could do it. So a big part of what we worked on is actually the compile time and the runtime software, which does the resource management, so humans are not involved. That way we can actually run 5 or however many you want, different applications simultaneously with dynamic loads. We can introduce new applications dynamically. It kind of interacts like you're just interacting with a general processor, although functionally it's completely different, right? Big part of it, like half the program was actually on the software side. And we have been trying to figure out how we can integrate the work we've done with GNU Radio. So this is, we have been thinking about this. We have a second program. We're not as far along in this one. We're now, on this one, we're doing basically a special modem processor for optical communications, in particular for space optical. This is another DARPA program. On the previous one, by the way, ASU is the prime, I'm the PI, but lots of great people are involved. It's also true, this one. I guess you can't see because the words are all over the top. My colleagues are all there from University of Michigan, from University of Arizona, from University of Wisconsin, and from DashTech Integrated Circuits, which is a company we started out we started in order to support this work as well. And I guess I'm already running over, so I'll quickly finish this up. We have another project which we were doing some work with DARPA and now doing some work with Space Force. We're working on building distributed coherent systems. So in the lab, we currently have a demonstration of an array of radios that all work together like there was one single wired up system. The universe does not want you to do this. So we transmit. So in astronomy for a long time, people have been receiving signals in a distributed coherence fashion. In some sense, that's very hard, but easier than this. When you transmit, you have to be completely exactly phased aligned at the instant. You don't get to fix it later. That's the moment, right? And so we can do distributed coherent beamforming. We even can do other distributed coherent system things, which are really a lot of fun, but I'll go very quickly. And for Space Force, because no great surprise there, they're interested in doing satellites. We were thinking about the implementation of that for a group of small sats. All right, so I'll repeat this. The stuff that goes on here and thinking about how do we make it easy to implement lots of functions and software-defined systems is the right answer. Well, lots of people are already thinking about this. I just sort of encourage you to think beyond just communication systems, just sort of general RF systems. And then we need to do a lot of work of figuring out how we can make all this stuff a lot more efficient. And maybe one last point, just because my university would like me to say this. Anybody involved in companies here, we have a particular opportunity for doing sort of small startup projects with the university. So it's New Economy Initiative. Anyone in some company that wants to team up with professors, the state of Arizona throws in some money, the company throws in some money, and it's an easy way to start up sort of interesting research that's on the small side, but potentially higher risk and in the long term, hopefully higher payoff. That's it. Thanks.